Okay, we're going to talk about something called the van der Waals equation. So we have the ideal gas constant. The ideal gas equation. Let's look at that. The ideal gas law is PV equals nRT. This ideal gas law, right in the name, it says ideal. This is under ideal conditions. We can use this equation to solve information about gases. Well, there are some things that are not true at high pressures that do not allow us to use that equation anymore. And in those situations, we would use something called the van der Waals equation. So back in the previous lecture when we talked about kinetic molecular theory, there were 2 of the 5 postulates that are not true at high pressure. And once we get into high pressures, this ideal gas law is no longer going to be accurate. So let's just revisit those. So these are postulates of kinetic molecular theory that are untrue at high pressure. The first is postulate number 1. Postulate number 1 says that gas molecules are so small that their size is negligible. Well, that's not exactly true, because at high pressure, the volume of the gas molecule, the size, is not negligible. The second postulate that is no longer true is postulate number 3. Postulate number 3 says that the intermolecular forces between gas molecules is so small that it's negligible. At high pressure, the intermolecular forces of gas molecules are not negligible. So these are 2 things that we were assuming for the ideal gas law that are not true at high pressure. So now if we use the ideal gas law at a high pressure, we would not get an accurate value because of these deviations, these assumptions that we're making for the ideal gas law. So we have an equation that adjusts for these 2 deviations, and it's called the van der Waals equation. So here's the van der Waals equation. So before I write it out, I want to tell you what is going to change. So to adjust, we are going to change 2 of the terms. So the V term is now going to become V minus NB. The V in my ideal gas law is now V minus NB. I'll tell you what B is in a second. The P term is now going to become P, pressure, plus N squared A over V squared. That's what P is going to be now. So P and V get new values to adjust for these deviations that occur at high pressure. So we have 2 new terms. We have an A term and a B term. So this A term and B term, these account for the deviations from ideal behavior. They are specific to each gas. These would be published in a book somewhere. So for example, the A and B of carbon dioxide is different than the A and B of oxygen or nitrogen or any other gas. So you would need to know what is the A and B for each specific gas before you would be able to use the van der Waals equation. And those would always be provided for you, or you would get some sort of table where you could look it up. So let's look at an example. So I'm going to say use the van der Waals equation to calculate the pressure exerted by 2.00 moles of carbon dioxide that has a volume of 10.0 liters at 25.0 degrees Celsius. Okay, so we're going to use the van der Waals equation to calculate pressure. We're going to solve for pressure. So before we do this, I'm going to write out what the van der Waals equation is, because I told you that these two substitutions were made, but let's go ahead and write it out up here. So the van der Waals equation is going to be P plus N squared A over V squared, V minus NB equals nRT. So this is the van der Waals equation. In this problem down here, I'm going to solve for pressure. Just because that's what this question is asking me for. You do not have to do this, but I'm going to do this because I feel like it saves a lot of headache later. So I'm just going to rearrange this equation to solve for pressure. So I'm solving for this. I divided both sides by V minus NB, and then I had P plus N squared A over V squared, so I subtracted N squared A over V squared from both sides, and now I have this van der Waals equation rearranged to solve for pressure, and now this is what I'll use to solve the problem. Also, this problem tells us what the A and B values are for carbon dioxide. So for carbon dioxide, A is 3.658 liters squared atmospheres over moles squared. B is 0.04286 liters per mole. So now I have everything I need to use the van der Waals equation to solve for pressure. Okay. So I'm going to use this version of the equation right down here. So I'm going to say pressure equals N, I have 2.00 moles, times R, 0.0821 liter atmospheres per mole Kelvin, times T, 25 degrees Celsius. I need to convert that to Kelvin. Over V, minus NB so that's this part, minus N again squared times A over V squared. So that's the whole problem. That's the whole expression written out. Definitely solve these two terms separately and then proceed. So with this term right here, you should get 4.933 atmospheres minus over here for this term, you should get 0.146 atmospheres. And then overall pressure equals 4.79 atmospheres. So this is the pressure exerted by 2 moles of carbon dioxide that has a volume of 10 liters at 25 degrees Celsius. So something that I want you all to do is I want you to compare the van der Waals equation answer to the ideal gas law. So I also want you to calculate pressure using the ideal gas law. So using PV equals nRT, not using these A's or B's, and see what you get for pressure. You should get an answer of 4.89. But I want you to do that on your own and see what you get. So you should get 4.89, which is close. You'll see that the ideal gas law value, atmospheres, the ideal gas law value and the van der Waals equation are going to be close, but the van der Waals equation is more accurate. It's more correct because it's using these A and B terms that are adjusting for these postulates that we are ignoring in the ideal gas law. At high pressure, the volume of these gas molecules are not negligible. The intermolecular forces between the gas molecules are not negligible, and that's what A and B are accounting for. So the ideal gas law is less accurate, especially at high pressure. So you might see something on the exam that asks you to calculate the pressure both ways.